In this video, we work through problem 107 from the Larson Calculus text, 10th edition. Here's the problem statement. It says, stopping distance of an automobile on dry level pavement traveling at a speed v in miles per hour is the distance r in meters that the car travels during the reaction time of the driver plus the distance v in meters that the car travels after the brakes are applied. So your stopping distance is the sum of those two functions. V is our independent variable. It's the speed of the car in miles per hour. And then R is the distance the car travels in the reaction time of the driver in meters. And then B is the distance that the car travels after the brakes are applied. I know I just said that twice, but I know when I read this problem statement, the first thing I want to do is define those variables for myself and then define the stopping distance. They mention the stopping distance, but they don't label it, at least initially. But I did notice when I'm reading the problem statement that it says it's the sum of these two functions. So I wanted to remind myself of that, summarize that, and then sort of label my variables, V, R, and B. And then it says the table shows the results of an experiment. All I did to create this table was just go up here to this little plus sign and then choose table from the list. And then you can change this variable here to V. That's what I did. And then change this variable to R. And then just type in your values. So that you'd use V equals 20, V equals 40, and all of this is in the textbook. You just type it in for V and R. You can also do this on a TI calculator, but I like using Desmos because it's free. After I did that, this is what I got. Here is this column V, R, and B. These were all given in the textbook. And then we can plot those points. Here's our v-axis. Remember, that's the speed of the car. R is the distance the car travels during reaction time. B is the distance the car travels after the brakes are applied. And T is the sum of those. And the problem statement says, use the regression capabilities of a graphing utility to find A, a linear model for R, and B, a quadratic model for B. So when you look at this set of points for R versus V, so that distance the car travels during the reaction time of the driver as a function of that speed that the traveler is going in miles per hour. This is what we get. When we plot those points, it looks like a line. And so it makes sense that the textbook author has asked us to find a linear model for R. I actually wasn't sure how to use the linear regression capabilities on Desmos. So the first thing I did, I just went to Google and I searched for it. I searched for Desmos linear regression, and I came up with this. So I just copied and pasted this person's code. They just use a tilde. They say the dependent variable is associated with this linear function. And when we do that, when we type this in for the particular variables that we're interested in, Desmos does all the calculation for us. So we were saying that our distance traveled during reaction time is just basically y equals mx plus b, but instead of x, we're using that v for speed of the car. And turns out our slope is 0.417, and our b value is negative 0.02. So it looks like this. Notice that that line goes through the points almost exactly, at least with this window. So that looks pretty good. And then it says, find a quadratic model for V. Now this wasn't actually on this website, but I said, okay, they want it to be quadratic. So I know I want it to be ax squared plus bx plus c, but we're using V instead of x. So I just typed that in on the right-hand side. And the graphing calculator actually came up with these values for us. So it's giving us the coefficient of v squared. It's giving us the a, b, and c basically for this quadratic equation. Oops, let's plot those points for b. I guess my point was, we look at these points, it seems linear. So they ask us to find a linear model. We find it, and we're like, ooh, look, it fits. That's good. And then it asks us to find a quadratic model for B. So let's plot those points. And that does look like a parabola. So it makes sense that we would choose a quadratic model for that. So just make a quadratic function in V on the right-hand side. And that goes through the points exactly as well. And then the problem statement says define the stopping distance t as the sum of r and b and determine the polynomial giving t of b. So the way I did that was I created a new column in my table. We already had r and b, so I just added those two together. I'm having trouble getting Desmos to do the calculation, so I just had to type it in. I just did 8.3 plus 2.3 in this cell here. And that gives me my values for t. Just adding the two values in these two columns. We could use Excel for this as well. We get these values here. Graph looks nice. And it says, define the stopping distance t as a sum of r and b and determine the polynomial giving t of b. So we know this is quadratic, the other one's linear. We would assume we can use the statistics calculator to come up with another quadratic model because a quadratic function plus a linear function is going to be quadratic. You can just add the ab squared plus bb plus c to the mx or mv plus b from this one, and you get the appropriate coefficients for this one. And we see that that parabola passes through the points really nicely as well. Now, in order to make this a function, I actually had to type some kind of subscript here. So I just typed t sub function because otherwise it's just treating this as this t value as a list of points. It's not really treating t as a function, even though it's graphing it as a function. So I wanted to graph the curve. So I just typed in my a times my b squared plus b times my b plus c, just copying down those coefficients from here. You see it's the same graph. And then it asks us to compute t prime at b equals 40, 80, and 100. Now to compute t prime, we could just take the derivative of this using our calculator if our calculator had that ability, but at least the way it is at the moment, I can't just type t sub function prime and have it give me the right answer. This is just a constant times v squared plus a constant times v plus a constant. So we'll take the derivative term by term using the power rule. So we're gonna have our constant times 2, that's our exponent, times v to the 1 less power, and we get this. And then the derivative of a constant times v is just the constant, and the derivative of a constant by itself is 0. So I just did that calculation. I actually used Desmos to multiply this by 2 and then typed in the number here. And so this is giving me my derivative function. Kind of difficult to see, but it's just a linear function with a very small positive slope of about 1/100. And then we evaluate at t equals 40, 80, and 100. So this is a good application or a good application problem to discuss instantaneous rate of change, because when we compute that derivative and we plug in t equals or v equals 40, 80, or 100, we get a number and we can interpret that number. So we'd say, okay, well, what does that represent? Well, remember, this is actually dt dv. So we're going to use the units of the numerator divided by the units of the denominator, to help us interpret that number. So that the number above, let's say this, represents, well, we know it's instantaneous rate of change, right? The instantaneous rate of change. Did I spell that correctly? Instantaneous of t, which is the stopping distance, as the speed of the car increases by 1 mile per hour at, or when, let's say when, v equals 40 miles per hour. Let's just say our speed is 40 miles per hour. So really all I did was just remind myself instantaneous I had it spelled correctly. Yes. All I did was remind myself what that t prime actually represented. It's the instantaneous rate of change of the dependent variable in terms of the independent variable, and our independent variable was speed. I do want to point out that I used a subscript 1 here on our v because we were using that v for something else up here. The v values were actually given data, and these v values are just another independent variable. So I needed to distinguish the two, and that's why I had to add that v sub 1. But so we've got the instantaneous rate of change of the stopping distance as the speed of the car increases by 1 mile per hour when our speed is 40 miles per hour. So, okay, we just sort of like copied and pasted the name of the dependent variable in there with the name of the independent variable. It's like, let's actually think about what that means. It says, okay, if that we've got a number of 0.86, says, well, the instantaneous rate of change of stopping distance is 0.86 meters, right? Because the R and B values are both in meters. Or no, is it meters? I don't remember. Those are in meters. Okay. As the speed of the car increases by 1 mile per hour. So we're at 40 miles per hour. We're talking about exactly what happens at 40 miles per hour, not what happens when our speed is 41 miles per hour. But we're almost thinking of that time increment or that speed increment as our speed actually changes from 40 to 41 miles per hour, but sort of instantaneously, as opposed to like thinking of an average over that time interval. We say, well, what is, how much does this stopping distance change when our speed is 40 miles per hour? So we're driving 40 miles per hour. If the speed just increases by a little bit, if it increases by 1, well, how much will my stopping distance increase? Well, my stopping distance will increase by 0.86 meters, approximately, for every 1 mile an hour increase in speed at that point, at that particular speed when I'm already going 40 miles per hour. Does that make sense? So let's write that down. The stopping distance increases by approximately 0.86 meters for a 1 mile per hour change in speed when our speed is 40 miles per hour. And then we do the same thing at v equals 80. So I'm just going to take that last sentence there and I'm going to copy and paste it. The stopping distance here increases by 1.31 meters, approximately 1.31 meters for a 1 mile per hour change in speed when our speed is 80 miles per hour, because that's what that v equals 80 means. And then for 100, just change that speed to 100, we get 1.53. The stopping distance increases by 1.53 meters for a 1 mile per hour change in speed when our speed is 100 miles per hour. So we're going very fast, 100 miles per hour. We're gonna go from, imagine going from 100 miles per hour to 101 miles per hour. Well, then our stopping distance would have to increase by 1.53 meters. So like that's how much space you're gonna need between the cars just to make sure that everybody's safe. Just does that make sense? And we look at these three numbers. When our speed is 40 miles per hour, the stopping distance was 0.86 meters. When the speed was 80 miles per hour, the increase in the stopping distance, was 1.31 meters. And then when we're at 100 miles per hour, the increase in the stopping distance was 1.53 meters. So we're really looking at those units in the numerator, but we're saying for every 1 mile per hour change in speed. So you want to make sure that you're still thinking of that in terms of both the numerator and denominator of that rate of change expression, because this is really a slope. Like geometrically, it would be a slope, and it's always the change in the expression in the numerator divided by the change in the expression in the denominator. So it's in terms of the numerator, but it's as that denominator is changing. So we want to make sure that we keep that the speed where we're calculating that derivative in mind, and the fact that we're imagining that it's increasing by 1. Because when we compute that rate of change, if you get like a slope of 3, we're saying that y increases by 3 units when x increases by an implied 1 unit, right? So we're going to use an implied 1 unit in miles, or an implied 1 mile per hour for all of these sort of denominators here. So the question after this, it asked us to compute those 3 derivatives and then interpret them. We've already interpreted them. It's basically, if you're speeding up, you're going to need more space in front of you to stop. And it says, what can we say about the total stopping distance as speed increases? We just said that. We answered that question. That was from the textbook. We can graph tangent lines as well. I don't know. I'm just a big fan of graphing all the tangent lines. Like, oh, look, it's tangent to the graph. So that's always a good way to make sure that we did our calculations correctly. And then we also were asked in the textbook, I didn't type this in the on the graph on Desmos here, to graph all 3 curves on the same set of axes. So here are our values, and trying to remember what R was again. The distance we travel in the reaction time of the driver, and then the B values for the distance the car travels after your brakes are applied. So that's this quadratic expression. So reaction time is just increasing linearly with speed, but our sort of braking, or the distance the car travels after the brakes are applied, like that's increasing quadratically. And then we add them together to get our total stopping distance. That's it. That's how we compute, interpret the derivatives as an instantaneous rate of change in a real world problem. And now you know how to use Desmos to do some regression problems when you want the function to be linear, quadratic, super easy. And I actually just learned that today by going to Google and searching for linear regression. And I found this and just copied and pasted. Super easy.